Hello everyone, welcome back to my channel. So today we are going to look into a recent paper called Learning Speech Representation from Raw Audio by Joint Audiovisual Self-Supervision. And the authors are Abhinav Shukla, Stavros Petridis, Maja Pantic. And this paper is a collaboration between ICL, Imperial College of London, Samsung, and I think Facebook. So, so the tutorial, we are going to first cover the overview of the paper, basically the abstract. Then we will see the proposed approach in detail. Finally, we'll see some experiments and results. So the idea, the paper itself says something called audio visual self-supervision. So you may be hearing about this self-supervision in these days, because this is become very hot topic these days, and many papers have been published on how to do self-supervised pre-training for audio or computer vision or even for NLP, right? And very few work is done in case where learning or working on the self supervision using both audio and visual modality, or as a matter of fact it can be any other modalities as well, like for example text and video, right? So this paper basically proposes this approach of cross modal self supervised learning. We will see how that is done in the coming slides. And that is one idea. And second thing is, they say how to use a raw audio as an input to a convolution or convolution encoder to learn the features directly from raw audio. And how do you use that in combination with visual self supervision, and to get the best out of both the worlds. And then you can use that self-supervised model or pre-trained model for some other tasks, like for example like word classification, in this spoken word classification in this paper, right? So basically what is the idea? So the idea is both audio and video will have informations which are related to each other, right? So these are even though they are two different modalities, they interact with each other when there is when there is a particular form. For example, let's say you are looking at somebody who is playing guitar, right? So there are sequence of frames, right? These are image frames, and you have the audio signal, right? So assume that I am not going to show the image part and show you only audio part, and you can say, okay, this is somebody playing guitar, right? Because you know the sound. And also assume I am not going to show audio, but I'm just going to show the sequence of frames where somebody is holding a guitar and doing some actions, right? And you can say, okay, that person is playing guitar. So that means these two modalities share some common information among them, right? So how do you leverage that information? How do you leverage that idea so that you can train a self-supervised model which will use information from both modalities to get a better pre-trained model which captures information about, let's say, phonemes or some other features which are helpful for downstream speech recognition task or language identification tasks, right? So that is the idea. So we will see this how do they do that, how do they capture the interactive information between the modalities, all those in the coming slides. So that is the idea. And the performance, if you look at it, so they get a competitive performance with respect to other self-supervised algorithms which are existing for speech, at least, right? So for example, there are many self-supervised algorithms for speech, like there is a standard CPC based method, there is something called APC based method. So CPC is basically contrastive predictive coding, and there is something called autoregressive predictive coding, and there is something called PACE which is called problem agnostic speech encoding or something, and space plus plus is also there, and then you have like wave to vec, which is also some sort of which uses which uses the CPC, but it has its own architecture. So wave to vec is one, and there is something like wave to vec plus plus. So like this, there are many methods. Like recently there is something called MPC, mask predictive coding, something like that. So there are various algorithms, and this paper compares all these algorithms with the current one, see the audio visual self supervision, and they get almost the same accuracy. We'll show you the results in the coming slide. But so and you can use also, they show that you can use this self-supervised model for downstream tasks, right? So let's look at the proposed approach, basically the idea of this paper in multiple sections. So first I will show you the model architecture. The diagram is very big, but I'll explain you what part of the network is responsible for what task, and then we will see the audio encoder architecture in detail. Then we will see how visual self-supervision and audio self-supervisions are applied, and at the end we will see how they are actually combined. So you can look at this visual self-supervision separately, and you can also look at this audio self-supervision separately, but the main goal of this paper is to combine the two, right? So this is the model architecture. So basically you can see there are so many things. Basically there is a sequence of, there is a audio part here, sorry, video part or visual part you can say, and here is the audio part, right? So from the same authors there is another paper which is exactly the same, but except they don't use raw audio, they use MFCC. You can refer to that paper. It's a previous to this, previous version of this paper, but anyway. So so the idea is similar, but so what is happening is you have two streams, right? You have two different streams. So one is basically going to take video, means image, and then another one is going to take audio. So let's first look into the audio part, right? So the audio basically takes 16,000 samples. So what is 16,000 samples? If your audio sampling rate is 16 kilohertz, you can say this is 1 second worth of audio data, right? So take this 1 second worth of audio data, feed it through something called 1D ResNet. So 1D ResNet is basically, you can think of it as 2D version of ResNet, but instead of using 2D convolutions, you use 1D convolutions, right? So as simple as that. And so why they use 1D? Because your raw waveform is 1D signal. So you can apply only one dimensional filters because it's only time axis is available. And once you apply let's say one filter to this, let's write this. So let's say x of t is your audio sequence, it has a lot of samples, and h of t is your filter, one filter, and when you apply do convolution, x of t gets convolved with h of t, you get another sequence y of t, which is also 1D, one dimensional signal, right? So that's why, so all the layers will look into this 1D convolutions, because outputs of every layer is one dimensional signal, right? And at the end you do average pooling, just like in the ResNet. Then you get one embedding, right? And this embedding is basically 512 dimension, and there is this 25, right? So this 25 basically tells you the time dimension. So when I say 500, so we can think of this 512 as number of filters, right? Number of filters in this at the end of this convolution layer is 512, and the timestamp, the number of frames you have is 25. So I mean this is where a lot of people gets confused, and I have even got a lot of questions from many people because some of my papers are based on this idea itself, like how do you leverage or raw audio directly for tasks like language identification, gender identification, so on. And I have a couple of papers in one in interspeech and I think one in ICASP. So basically why people gets confused is like this. So let me explain it in detail so that everybody understands this. So let's say you have one dimensional signal, right? And you have 1D filter, right? Filter is h of t and your sequence is x of t. Now when I apply this, I get another sequence, right? Let's write it as y of t, right? that is only one filter, but usually in CNN's convolution neural network you have a lot of filter in the sense, let's say 64 filters like this, but they are all different values. Then you get another signal for second filter, another signal for third signal, and when you look at this becomes like a matrix, right? You can think of it as a matrix where this dimension is 512 and this dimension is t basically. But based on the filter weights and filter shifts and so on, your time will keep reducing, and that's what happened here as well. So at the end you got 512 and you got 25 times frames. So the filters are designed in such a way that, I mean, they are actually chosen like the width of the filter and kernel's size and kernel shifts are chosen such a way that for this 1 second you will get only 25 time steps. Why? Because there is another reason why, because you want to sync this output with the visual part. So we'll get into that, but assume your output is 512 cross 25, right? Now you have to so let's look at this part later, but now what I am going to do is I'm going to explain you the visual part. So the idea of visual self-supervision here is, given the first frame or a 0th frame, you want to predict the future, right? You want to predict the next consecutive 25 frames. This is similar to something called CPC. So CPC, basically the idea is, given a feature which is a feature at the time step t, you want to predict next 10 time steps in the future, right? All the feature vectors for the next 10 time steps. So that way you are capturing the relationship between, or you are capturing the local information within the audio, like the local information which is important for, let's say, phoneme, right? So this is not a new idea. I mean, this has been done long back. If you look at Vishnu et al.'s the famous work on linear prediction coding, LPC, it's actually almost the same idea, but it's just kind of neural network way of doing it, right? So then the same way, so basically what these people are doing is they are taking the first frame and try to predict the next 25 frames in the future, right? So what they are going to do is very simple. You take the image, first image, feed it through some 2D convolution, and at the end when you get some feature vector for that image. Then using this and the feature vectors from audio, you can then generate the new 25 frames. You can ask a question, this dimension of this, I mean this is only one dimension, for example. This has 25 time steps and at each you have 512 vector. How are you going to handle this? Very simple. You take this and replicate this 25 times, right? So basically this ZID is also a matrix of, let's say, 64 and 25. Now you just have to concatenate the visual ones, 512, 25, right? Very simple. Just concatenate, then use it to predict the future frames of this particular image, right? 25 future frames. That's all. That's the idea of the architecture. It's as simple as that, right? You have the model. I told you what is the ingredient. It's just you take the image and try to predict the future. You take the audio, but in this case, you can ask me a question: how are you going to train the model, right? So first thing, for visual part, you need to construct a loss function. So loss function could be a simple reconstruction loss, right? So you just predict the future frames. So in fact they are not using CPC here, they are just using reconstruction loss, but they should have used CPC, because I think those are better than L1 loss. So you take the L1 reconstruction loss, then that is for the image part. But for audio part, you can do these three different things. This almost looks like a paper named PACE, right? So PACE basically is a work from Yosho Bengio's lab by Mirko and a few other colleagues. So basically what they say is, if you want to train a self-supervised audio model, you take the raw audio, feed it through some syncnet and convolution layers, then you predict the audio attributes, right? When I say audio attributes, there are many of them. So one is the pitch, another one is gain, another one is duration, those are like called prosody parameters, and you can always go for other parameters like MFCC, spectral features, and they have few other fancy loss values, I mean attributes, and you can train the model because you don't need any supervision there. I mean, you don't need any label data there because everything you have, right? You have the audio, and you can calculate pitch using some signal processing algorithm. You can always compute energy, and you can compute all others, right? You don't need any label data for to train that model. But once you train it, you can use that model as a pre-trained network for some other downstream tasks. But in this case, they are actually using almost the adaptive version of PACE, where they don't use all the features, all the attributes, but they use only 3 attributes, which is called waveform decoder, log-mel decoder, and MSCC decoder. Basically, what they do is from this representation which we got, they are going to construct the MFCC, and they are going to construct the log-mel, and they are going to construct back the raw waveform, and they compute the reconstruction loss for each of them. They add that reconstruction loss for audio with the reconstruction loss for video. That is the final loss. Then you use this loss and back propagate through all these models and train the model end to end, right? As simple as that, right? So I think they should have done some more ablation studies, because what happens is these they should have done some ablation studies saying, okay, what is the effect of this, what is the effect of this, what is the effect of this, like that. Because what I think is, because this predicting, when you predict the raw waveform, you are obviously you are going to take the difference between the raw waveform and the the original, right? That is yeah, I mean, never mind. I was thinking maybe they are computing some sort of an energy of the audio, because it's not actually energy, because they are just computing difference between this signal and this signal. So energy is basically computing within this. So yeah. Anyway, so what I meant to say was computing difference between this audio and this audio is kind of finding the energy, right? Difference between the energy of this signal, but that can be easily captured with MFCC or log-mel, because the first element of MFCC actually represents the energy of the audio, and anyway you are predicting the energy, and you know the ground truth energy, you just anyway taking combination. So what I'm saying is this is kind of redundant. That's what I was actually thinking, but I don't know, maybe if they do some ablation studies, they may be able to find out what is the importance of this particular attribute, right? So this is the whole idea of the paper. So let's go into the details. So as I said, the audio encoder part you saw, so it uses 1D ResNet as a backbone, and it uses 1 seconds of audio data, which is 16,000 samples, and the output is 512 dimension, and D is 512 dimension audio feature vector for every time step, and there are 25 time steps. That is to match with the frame per seconds for the video. So and we'll see the data set in the coming slides. And so yeah, that's the part of audio encoder. And as I said, for the visual self-supervision, they are using all the 3 model, and they are concatenating the audio encoders hidden embeddings. I mean Z, we have the ZA, which is the audio embedding, and we have this Z, I think it is ZID, which is basically the hidden embeddings from the visual part, and they have to just concatenate these two, right? And they feed that to the frame decoder. Frame decoder is basically the decoder, which is basically the inverse convolution layers, which generates the future frames, right? And L1 reconstruction loss is used, as I said. I mean, that's a simple thing. And if you look at the self-supervision, sorry about the typo. So what they are doing is as simple. So FA is basically the ResNet 1D ResNet audio network, and you can think of it as some sort of a functional mapping of the input audio. Then for the image part, you have this other functional mapping, which is the CNN again. Then these representations ZA and ZID you concatenate. Cat is basically the concat operation, and then you use that along with the original image to compute the final prediction, and you know the ground truth, and to take the L1 loss. So they are taking L1 loss instead of L2. The reason they say is because they want to get sharp edges. They don't want to blur the image. They want the sharp edges in the prediction. That's the reason. And In case of audio self-supervision, it's very simple. As I said, they are predicting three different things. One is MFCC, another is log-mill spectrogram, and another is waveform. And you can call them all of them together as some sort of a attribute list, and you predict all the attributes list, and you know the ground truth. You just compute the L1 loss again. I don't know why they use L1 here, because they should have used L2, something like that, because you are not looking into sharp edges in the reconstruction here, right? Because it's audio, it's not image. But anyway, so at the end, to train the model end to end, you just add the video loss and audio loss, and then you do back propagation. As simple as that. I hope you guys understood. I mean, it's not so complicated to understand. It's a bit simple once you understand it. So let's look at the data set. So the data set is LRW, lip reading in the wild data set, which is basically video clips of people speaking digits, or people speaking something, and you have the audio clips, and you have the video clips where the people's lip movements are there, and you know the audio track, and that is used for the dataset is used for something called isolated word recognition using lip movements, right? And it has all this, as I said, nearly frontal videos and all these things. And they take the subset of that LRW, full LRW data, which gives you around 40 hours of usable data, and then they train the model using this subset, the self-supervised model, and then they use this speech command data set for spoken command detection, which is a supervised task. And I think I didn't show you the testing model, where the testing model is very simple. You take the model, the pre-trained model, and then you attach this bidirectional GRU on the output of the bidirectional GRU to this ZA. I mean, basically you feed the ZA to bidirectional GRU, and then do all the supervised training, right, of that. And learning rate is this, and they use the training for 40 epochs, and the last 10 epochs they reduce the learning rate, right, and they use softmax and cross entropy loss. Very well, let's come to the experimentation results section. So basically this should have been results. Sorry about the title. This is actually not experiment. This is basically result section. So in the result, as I said, they have compared many methods. First, they just use the plain MFCC, and they don't mention whether it's self-supervised or supervised. But anyway, maybe it is supervised completely. So they get on SPC speech command detection, they get 95% accuracy, and if they use only 10% of the label, the accuracy reduces a little bit, right? And that is known thing. And on LRW, if you use the full data, you get very good accuracy, but if you reduce it to only 10%, you get worst. That's very bad, right? And PACE, if you look at it, PACE is the as I said, the Mirko and Yoshua Benjius labs and collaboration between some other universities. You get 95% if you use full data, and if you will get only 83% if you use only 10% of the level. That means it is doing something. I mean, the PACE model is capturing some information, but not as good as using the just MFCC. So yeah, and same thing happens on I mean, in case of LRW, it's worst. They get only 1.8% of accuracy, which is like, I'm surprised. Maybe this number is wrong. I don't know. Maybe I should speak to the author, but 1.8% is like a very bad number, right? So if they use APC, so APC is basically the autoregressive predictive coding. It uses, again, it tries to predict the future frames using autoregressive fashion instead of using contrastive loss. They get very good accuracy if they use the full data, and even if they use less amount of data, basically 10% of the data, they get very good accuracy. 89, approximately 90% is a very good number. And same thing happens with LRW as well. Results are good, right? And wave to wake is actually, I would say, it's the best, because it is going to work very well on full data as well as on the on the 10% of the data. But in case of LRW, it is not working well. L1 loss, it's actually the same paper, same guys, same authors of the same paper. It's a previous work. They use the MILF features, but they don't use their audio, but okay results, I mean good results, not okay. So this paper, the L1 plus odd, which is the uh, sorry, this basically the previous one with audio visual, the previous paper with visual, so they get this much amount of accuracy. And if they use the current this paper's accuracy are like this. If they use only audio, they get good numbers on both LRW and on SPC. Using only visual, they get good accuracy, and using both audio visual, they get the best. And if they use fully supervised training, completely supervised, they get this result. And if you use only 10% of LRW, the results are not so good. Coming to the experiments for the SPC, spoken word classification. If they use different types of noise, what is the accuracy? I mean, you can take a look at the table, but yeah, this is one sort of what is how the models are robust against these noise levels. And that's all for this tutorial. So I am actually working on writing implementation of this paper. I think it should be done in this week. I think I will publish that code in my Git repo. I think you guys can take a look at it. And yeah, thank you so much for watching this tutorial. If you like the video, please give a thumbs up, and if you are not subscribed to my channel, please subscribe for more of these kind of tutorials. Thank you.